Lecture 16, Norton's Theorem, Concept and Solved Example. So why do we require Norton's Theorem? So similar to Thevenin's Theorem, if in a complex circuit we are only concerned with load resistance or current through it or voltage across it, then it is not beneficial to solve the entire circuit. So using Norton's Theorem, this entire circuit can be reduced into a simplified circuit which has current source in parallel with Norton's resistance while the load terminals remains unchanged. So let's understand Norton's theorem by solving this numerical using Norton's. So these are all the steps involved in solution of this numerical using Norton's theorem. Let's move on to step 1. The step 1 is identify load and short it. So this 3 ohm resistance is the load, so we will replace it with a short. So this can be represented like this. Now due to the short, this 6 ohm resistance will be bypassed. Therefore, if I dash current is flowing through this branch, the entire I dash will flow through here and the current flowing through this 6 ohm will be 0. Therefore, I dash is simply equal to IN. Next step is to find out this short circuit current IN. So it can be found out with the help of nodal analysis. Suppose this is the reference node and V is the node voltage, then this IN will be simply equal to incoming currents, that is 4 amperes plus, suppose this current is I, so therefore plus I. Now IN can be written as V by 3 is equal to 4 and I can be written as 15 minus V by 3. Rearranging this equation, V will come out to be 27 by 2 volts and IN is simply V by 3. Therefore, IN is equal to 27 by 2 into 3, which comes out to be 4.5 amperes. Next step is to find out the Norton's resistance. The first step in this is open circuit the load terminals. The next step is replace the current sources by their internal resistance. So ideal current source has infinite internal resistance, so it is replaced by an open circuit, and ideal voltage source has 0 internal resistance, so it is replaced by a short circuit. Now R equivalent is found out looking from this side, so we can see that these two resistances are in series, so they can be directly added like this. And finally, the R equivalent, which is simply Rn seen from these two terminals, is the parallel combination of these two resistances, which comes out to be 3 ohms. The next step is to draw the Norton equivalent circuit, which is having current source IN in parallel with the Norton resistance, that is 3 ohms. And the last step is to reconnect the load terminals, and IL can be found out with the help of current divider rule, which is IL is equal to I total, that is 4.5 ampere, into Rn, that is 3 ohms, divided by Rn plus RL. And this comes out to be 2.25 amperes. Final part, Norton equivalent circuit can be converted into Thevenin equivalent circuit, with R Thevenin being same as that of Rn, and V Thevenin is equal to IN into Rn, which comes out to be 4.5 into 3, which is 13.5 volts. Homework question: apply Norton's theorem and find out the value of Norton's current source and Norton's resistance across load terminals A and B, and post your answers in the comment box.